Fede, si sente?
Sì.
Ok, grazie. Okay. So last time we finished with the Fermi-Dirac distribution and the properties of gas of free fermions. Now let's make a little exercise on this part, and let's consider let's consider this physical effect, which is called the thermolionic effect. So emission of electrons from a metal from the surface of a metal, for instance, as due the heating up of this metal, okay, due to the heating. I don't know if it's something that you have considered already in other courses, but let's make this exercise, which is an application of the Fermi-Dirac distribution, basically. Well, actually, not really, in the sense that at some point we will use the Maxwell distribution in order to make calculations simpler. Okay, so for instance, this is the fact that you are heating up a metal and then you have release of electrons. Okay, so how does this mechanism work? So basically, the idea is the following: we have here the energy of our electrons, and here we can think about the crystal, the lattice of ions, as producing a sort of potential well that is in which the electrons are immersed somehow. Okay, so they occupy all the energy levels of this potential, negative potential, up to the Fermi energy at equal 0. Okay, so if you want, this is the Fermi energy, which is equal to the chemical potential, and we suppose that this is correct, even if we are not at equal 0. So we assume that all the energy levels are occupied. And there is a gap here, which is called the W, work function, called. Which is the energy required in order to take an electron from the Fermi surface and promoting it to the continuum of levels. Okay, so this is the energy required to, if you want to remove an electron from the metal. Okay, so you have to provide this amount of energy in order to take an electron from here, from the surface, from the Fermi surface, and to make it free to move in space. Okay, and of course, in order to do that, the kinetic energy, suppose that here this is the metal, and this is the x vector. The kinetic energy, the component of the kinetic energy in the direction orthogonal to the surface, let's suppose that is x, must be larger than W plus EF. So we have to impose that the kinetic energy the component in the x by component, I mean the contribution, the kinetic energy provided by px squared divided by 2m. And we want this energy to be larger than basically this jump, which is EF plus W, okay? Where we are considering all the possibility to remove all these electrons also from below the Fermi surface, okay? So we require this kinetic energy to be larger than epsilon F plus W. And since we are considering EF equal to mu, which is valid at a small temperature, this must be larger also. This is mu plus W. Okay, so now the calculation can be done in the following way. So let me remove something here. Well, before we want to write down what we are going to derive, we are going to derive Jx, which is a flux of charge, density of charge current, which is equal to the electron charge times the density of electrons times here, in order to have a flux, so a number of particles, or in this case coulomb per time per surface, you have to multiply by velocity, which in this case we will consider to be the average velocity in the x direction, which is the direction orthogonal to the metal surface. Okay, so the average of velocity in x direction. Okay. So what we are going to compute basically just this average. Okay? Then E and N are given. And we have to compute this average by considering the Fermi-Dirac distribution and by considering this constraint on the kinetic energy along the x direction. Okay? So what we are going to do is basically provide an estimate for this average Vx. So let me remove this. And let's try to write down this average. So Vx, the average, is equal to the following. So as in the Maxwell-Boltzmann distribution, I have to compute the averages. I have to take the distribution, which is the exponential of e to the minus beta epsilon, times the quantity that for which I want to compute the average. So in here is going to work in the same direction. Just the difference is just that we have a Fermi-Dirac distribution. That's it. Okay. So this average is 1 over n, which is the total number of particles, of electrons in this case, total number of electrons, which, if you want, is the normalization. Then here we have G V divided by 2 pi h bar to the power of 3, where G is equal to 2 and is the generacy. And V is the volume, And this 2 pi cubed and h bar cubed comes from the integral over the momentum that I'm going to specify in a moment. So here I will have the integral over dpx, integral dpy and dpv. Those are from minus infinity to plus infinity for the y and z component. Whereas here you have plus infinity, and here we have a minimum of momentum, which we indicate with px mean, which will be provided by this condition, okay, by the fact that px squared divided by 2m, which is equal to epsilon x, must be larger or equal than plus w. Okay, so then we have a minimum momentum that we have to consider, and also this minimum momentum must be positive because we want to consider a velocity which is along the x direction and is pointing outside the body. Okay, so this px component is positive also. So px mean is positive, which means out from the body. Okay. And then here what we have to do, we have to average what the velocity. The velocity is px divided by the mass, and then we have to add the Fermi-Dirac distribution. So we will have 1 divided by 1 plus the exponential of beta times, here you have to include epsilon mu, epsilon minus mu, where epsilon is the sum of 3 terms, which are the 3 components, if you want, of the kinetic energy. No? So epsilon is epsilon x plus py squared divided by 2m plus pz squared divided by 2m. Okay, so this is the formula that we have to compute the average energy. Now we have to do some assumption in order to make the calculation, to have some analytical results. Otherwise, we can already stop here. Because when we have the Fermi-Dirac distribution, it's a little bit complicated to do the integrals. Well, it's not always analytical, not in this case. So now, what we are going to assume is that we can assume that epsilon x is larger, so let's write it down. Epsilon x minus mu is larger or much larger than w. Larger than w. And if we suppose and assume that w is much larger than t, this can be, well, this condition corresponds to the fact that the kinetic energy must be larger than mu plus w, as we wrote here, in order to make the electrons free. And we are assuming that the work function is much larger than the temperature, which is a reasonable assumption in the sense that at room temperature, electrons are bounded in our metal, and I have to provide heat in order to release these electrons. So I can assume this. Now, if this is true, then I have that epsilon x minus mu much larger than the temperature, and therefore this exponential is large, and I can approximate the Fermi function as Maxwell Boltzmann distribution, which is e to beta mu and e to the minus beta epsilon. Okay, just because this epsilon x, which is a component of epsilon, minus mu is larger, much larger than kBt, and therefore this exponential explodes. I will have a Maxwell-Boltzmann distribution, which is provided by this term, with the additional factor, which is a exponential of beta mu, which is not present in the Maxwell-Boltzmann distribution, that was derived in the microcanonical ensemble, or in the canonical ensemble. Good. So now, basically, in the integrals that we have there, you can make this substitution. And so, if I am alone, I will do like this. I have the exponential of, let me also divide the different components. So one of these is epsilon mu minus epsilon x divided by kBt, which corresponds to epsilon x here. Then we will have two Gaussian integrals, p y2m kBt, and the exponential of pz squared divided by 2m kBt. Okay. Okay, now this is equal to V divided by N is just 1 over the density. So you have G divided by the density. Now you have a 2 pi H bar cubed. And then I can do the integrals of dpy and dpz. So those are Gaussian integrals. Because they are integrated from minus infinity to plus infinity of those two Gaussians. And I will get the usual square root of pi, and then 2m kBt. Okay, so I have this, which is pi 2m kBt to the power of 1/2 squared. Okay, coming from those two Gaussian integrals. No? So I have square root of pi divided by alpha, where alpha is 1 over 2m kBt. So I have 2m kBt. Okay, so then I'm left with the integral over dpx. We have plus infinity and px mean of the exponential, which can be maybe taken outside. Okay, let's do it afterwards. So here I have px divided by m, and the exponential of minus ex divided kBt, and then everything is mu. Okay, now I have to do a short change of variables. So let me, okay, epsilon x is px squared divided by 2m, and therefore d epsilon x is 2 px squared, sorry, 2px dpx divided by 2m, and it drops. So then when I see px dpx divided by m, I can just write this as integral over d epsilon x. And where is running this integral? Here the plus infinity. And here I have the minimum of epsilon x, which is w plus mu. Okay, so this is the minimum value. Okay. Yeah, and then I have just exponential of epsilon x divided by kbt. Okay. Good. Now I can do this integral. So this e to minus epsilon x divided by kbt. Then I have a minus kbt. And this must be computed from w plus m, w plus mu, sorry, and plus infinity. Plus infinity goes to 0, and to w plus mu becomes w plus mu. So I have the exponential w plus mu. So finally, we have this expression. So this average of Vx is provided by G divided by N. Then there was 2 pi h to the power of 3. Yeah. Then there was this term here, which is 2 pi m kbt. And that's it. Then I have the exponential E mu divided by kbt. And then I have this integral finally, which is a kbt, and the exponential of minus w minus mu divided by minus w minus by kbt. And I think I have everything there. Let me check. Okay. Okay, that's everything. Okay, so here now we can make some, let me see, il 2 pi forse lo semplifico, no, lo lascio là. For the moment, I like this. So it's 2 pi, and I have a kbt to the power of 2. Then I have the exponential of minus w divided by kbt. And here I have, well, I have a g, n, and h bar is a constant h divided by 2 pi, so this is just it's cubed. And maybe it's better to leave it like this. And now considering the fact that Gx was electron charge times n times Bx, I have a density that must be multiplied there, and therefore drops this density. Then I have G is equal to 2. And then finally, I should get 4 pi m, 4 pi e m divided by h to the power of 3. Then I have a kbt squared exponential of minus W divided by KBT. Making this time. This is called the feature from migration. Okay. Now some comments about this formula. What is important to notice is that we have an exponential suppression in which we compare the work function and the temperature as usual when we have a gap in the spectrum. Here W corresponds to a gap, so it's the difference between equal 0 and the Fermi surface. So we expect to have this factor which is corresponds to the excitation of degrees of freedom which have a spectrum, a gap in the spectrum. And then we have part of the prefactor, we have a KBT squared, which of course is important, where this KBT squared comes twice of them. Well, one of them, 1t, was coming from the two Gaussian integrals, so the fact that we are integrate over dpy and dpz, and the other one comes from the integration of px divided by m over well, with the Maxwell-Boltzmann distribution, basically. Okay. So, okay, this is both just an application of the Fermi-Dirac distribution, although at some point we have made the assumption of epsilon minus mu much larger than KBT in order to make the calculation easier. Now let's move on. We close this part with Fermi-Dirac quantum statistics. So now the last part of the course would be about phase transition, particular second order phase transition, critical phenomena and stuff like that. Now, last year I have done more about this. This year I decided to be a little bit slower, and so therefore, for instance, last year I was applying the Fermi-Dirac distribution also for computing the Landau diamagnetism. This year I will jump this part, and but you are unfortunate because you have a written exam with respect to the other ones, but the program is a little bit smaller actually. Okay, I will jump some topics. Now, next topic is the Icing model. Già morto. Sembra che si asciughino. And in particular, we will start with the Icing model in one dimension. What is the Icing model? It's a very interesting model that make at least easy to understand the features of second order phase transition. For instance, in magnets in particular, what is the critical temperature? And this is just a model. It's a very simple, it's the easiest model actually, but one can learn a lot of things about this model. Okay, and it works as follows. Well, first of all, we will start with one dimension, and we will see, I anticipate that in one dimension there is no phase transition within this model, whereas in two dimensions there is a phase transition that we are going to compute by using an approximation, which is called Midfield Approximation. Okay, this is the standard way of presenting this model. Okay, so the model basically, with respect to what we have done until now, introduces. So we have independent. Well, we have localized particles that we can think about as having a magnetic moment, which can interact with an external field, but which can also interact among them with themselves. So this is important. So we are introducing interactions. And once we introduce interactions between particles, we can have phase transitions, critical phenomena, etc. As we saw, for instance, for the case of a gas of classical particles, when introducing the interaction, we have seen the virial expansion that we can have already the van der Waals gas, and so the features corresponding to phase transition. Okay, so the model actually has been used already during these lectures when considering the way to pass from statistical mechanics to thermodynamics, and basically it's a spin model in which we are thinking about a linear chain of spin which can be up and down, so two possible values, etc. Okay, and this so since this is a linear chain, so in one dimension, we assume that each of these spin of this particle interact with only one, with only two spin, which are the closest ones. Okay, so therefore the starting point is to write the energy, or the Hamiltonian, if you want, of this linear chain that is assumed to be like this one. I'm going to write first and then I will comment. Okay, so what are these quantities? Epsilon is an interaction strength among the spins. Sk is the spin of particle K, and it can have two values, +1 or -1. Okay. And H is an external magnetic field. Okay, so this Hamiltonian, how does it work? Basically, if two spins, and here I'm coupling just Sk with Sk +1, which means that each of them interacts with only two other spins. Okay, so each spin interacts with two other spins, which are the closest. The closest ones. I primi vicini. And what happens that if they are aligned, so if they are plus plus or minus minus, then I have an addition. Well, I have a negative contribution to the energy, which means that it's good because minimize the energy. And whereas if they are misaligned, so if it is plus minus or minus plus, you have a positive contribution to the energy. So this, from the energy point of view, is not good. Okay, so we minimize the energy when all of them are actually aligned, as it is very intuitive to understand. And now for this term, instead, is the same in the sense that suppose that but we assume that if they are plus, so if they are in the positive direction of z, for instance, they are aligned to the magnetic field, and therefore we have a negative contribution to the energy, whereas we have the opposite if they are in the other direction. Okay. So as usual, if you have a magnetic dipole and you have an external field, you minimize the energy when the magnetic dipole and the external field have the same direction. Otherwise, we have a positive contribution to the energy. Okay. Good. Now, I think I said everything about this. And now let's make this assumption. So here we are, first of all, we are conserving the number of particles, and therefore we are going to work in the canonical ensemble. First of all, we are working within the canonical ensemble. And in order to make the calculation easier, we do not like what happens at the edges of this linear chain, which is S1 and Sn. And therefore, we are going to make the following assumption, that S1 is equal to Sn plus 1, which means it's like a periodic boundary condition, if you want, periodic boundary condition. So that means that once we arrive at n, so it's like having a sort of circular chain, in the sense that here I have 1, here I have 2. When I arrive to n, I will come back to 1. So S1 is equal to Sn plus 1. Now, we will see in a moment where this assumption is will play a role. Okay, just in a moment. Okay. So at some point here, we'll have a term which is Sn plus 1, which I know what it is. So I will just write that Sn plus 1 is just S1. That is like that the n term interacts with 1. Okay. But it's just a border effect. It's not very important for the bulk. We are just assuming something which is valid at the edges. So it's not going to affect what we have in the bulk. Yeah. Okay, so now it's the energy or the Hamiltonian is this one. Then we can write down the canonical partition function, and I will do it here. The canonical partition function will be made of several sums, where we are summing over the values of S1, S2, S3, and Sn. So here you have S1, sum over S2, etc., sum over Sn, which are the degrees of freedom here of this Hamiltonian. Then we have e to the minus beta h, which is e to beta. And then we have this guy here. So epsilon sum k1 and sk plus 1. Then I have plus h sum from k of sk and that's it. Okay. This is the canonical partition function. which has the form of something like this: S1, Sn. Here I have the Newtonian S1, Sn. Okay, and the Hamiltonian is diagonal because we have written already the diagonal form in S1, S2, S3, Sn, with terms that are provided by this formula here. Okay? But the structure is this one. It's a matrix element of e to the minus beta h. Now, since we have done the assumption on the boundary condition, we can slightly modify this canonical partition function. Here you have beta times epsilon sum from 1 to n of sk plus 1 plus h. And here I'm going to write the following: a1 to n of sk plus 1 divided by 2. And here I have 1 half. No, 1 half is diverso. No, sono messo tutto. What I'm doing here is basically an average, in the sense that here you have the sum of the single sk, and here I'm summing over sk, and I'm summing over sk plus 1, and I'm dividing by 2 in order to not to add another. No? So let me write it here. So you have the sum from 1 to n of sk plus the sum from k1 to n of sk plus 1. Of course, for all the terms, but from the n term, this is equal, if I take a 1/2, to the previous expression. And for the last expression, I will have, for the last term, I will have Sn here plus Sn plus 1 divided by 2, but Sn plus 1 is equal to S1 plus Sn divided by 2. And therefore, this is symmetric. So with respect to the previous expression, okay? Okay, so remember that it's 1 is equal to Sn plus 1. And so here we get basically Sn half plus S1 half. And S1 half will sum with this first S1 in order to get S1. Okay, so you can convince yourself that this expression here is equal to this one, as due to the fact that we are taking the boundary condition in a periodic way. Okay. Clear? Well, no, the first sum plus there is 2 plus Sn plus 1. But Sn plus 1 and S1 are the same, therefore we get the same S1, okay, divided by 2, twice divided by 2. Okay, good. Now, we can actually compute, and this is interesting, without any assumption, we can compute the partition function associated with this system, at least in 1 dimension. In 2 dimensions, one can also do it, but it's much more complicated. But before doing that, let me introduce a matrix that I call P, and this is the matrix associated with E to beta epsilon S prime plus H S plus S prime divided by 2. You will be clear in a moment what I mean and why it is useful to introduce this matrix. S primo, okay. So let's compute the matrix element of this matrix. So we'll have here S and S prime. And in particular, let's consider 1 P1. So I take S and S prime equal to 1. Therefore, here I will have E beta epsilon plus is 1 plus 1, which is 2 divided by 2, so plus H. Okay. Then we take minus 1, and here is beta. Minus 1 is still epsilon, and here I have minus 1, which is minus H, because it is minus 2 divided by 2 minus 1, minus H. And finally, we have a minus 1 P1, which is equal to 1 P minus 1, which is equal to E to the minus beta epsilon, because the term with the external field will drop. Okay. So in a matrix form, this P can be written as follows, can be represented as follows. So P has the following shape. So I have E beta epsilon plus H, E beta epsilon minus H, E minus beta epsilon, E minus beta epsilon. And this will be useful in a moment in order to compute the eigenvalues of this matrix. Okay. Now let me write down again Z of C, which was the sum S1, sum Sn of E beta, and here I have, okay, maybe it's good to do it in order to see what happens there. So let me make the two sums that we had before explicit, sorry. Here you have epsilon S1, S2 plus H divided by 2, S1 plus S2. Then I have plus epsilon S2 times S3 plus H divided by 2, S2 plus 3, on the other terms. And so here you see that I can basically consider these as the matrix element of this matrix P. So to be more clear, so this is the sum of S1 and sum of Sn of this guy correspond to the matrix element between S1 and S2 of the matrix P. So here I wrote SS prime, which are SS prime in this case, S1 and S2. So this is S1 P S2. The first term, so the first exponential, correspond to the matrix element between S1 and S2 of P. Similarly, for the other term, so the second term, again, is a matrix element between S2, P, S3, because we have 2 and 3 here. Okay. And we can move on until we arrive at Sn matrix element P, and here we have S1, because Sn plus 1 is equal to S1, as we have assumed boundary conditions which are periodic. Okay. Now, if you take now, for instance, the sum over S2 of S1 P, S2, S2 P, S3. What is this sum here? Here I'm fixing S1 and S3, and I'm adding all the values of S2. So this corresponds basically to a product of P by themselves, and I'm taking the S1 line and S3 column. Okay, so this will correspond to P squared, and from this P squared, I take the row S1 and the column S3. So this is the row index, and this is the column index. Okay. È il prodotto riga per colonna di due matrici. Okay. And I'm doing this many times, so many times, n times, because I have this guy, up to Sn. So I'm multiplying P by itself n times, and at the end, I'm summing over S1, which correspond to take the trace of Pn. Okay. So basically, what we have here, by noticing that if I take two of these factors, this corresponds to the product of the matrix P by itself. So basically, this canonical partition function at the end is just the sum over S1 of S1 P to the power of n, and finally S1. Okay. Now, what is this matrix element? What is the sum of this matrix element? It's just the sum of the diagonal terms in this matrix. So it's just a trace of Pn. Okay. It's really magic. That's why it's interesting to do it, because it's a situation in which one can compute analytically the canonical partition function, and one is very happy for that. Quite nice to do it. And though, as we will see, but this is also a very important point, in one dimension we will not have any phase transition, but it's a nice example in order to make also analytical calculation. Okay, so now the trace of Pn can be written as follows. The trace of Pn is the sum over the diagonal terms of this Pn. No? So if I'm writing Pn, well, if I'm writing P in a basis in which this is diagonal, P to the power of n will just be the matrix in which I have the two eigenvalues to the power of n, and if I do the trace, I just have the two eigenvalues to the power of n summed. Okay, so this is just suppose that I call lambda plus to the power of n and lambda minus to the power of n, where lambda plus and lambda minus are the two eigenvalues of P. Okay, so remember that the trace is something which does not depend on the specific basis. No, it's the trace is remains the same by unitary transformation. So we can take P, we diagonalize P. P to the power of n is just a diagonal to the power of n, and the trace does not care about the representation on a specific basis. So we can work in a basis in which P is diagonal, and therefore it has a very simple form. It's just lambda to the power of n, lambda minus lambda plus to the power of n. The trace is just the sum of the two eigenvalues. Okay. So now the next point is to compute the eigenvalues. And once we compute the eigenvalues, we have almost done. Okay. So let's do it. The matrix had the following form. So E2 epsilon, E2 beta epsilon plus h, e to the minus beta epsilon, e to the minus beta epsilon, and e to beta epsilon minus h. This was the matrix P. Okay. So now if I want to compute the eigenvalues, I just need to write down the circular equation. So into minus lambda times guy minus lambda minus equal to 0. Okay. Okay, so now it's a matter of doing the calculation. I'm not sure how in detail I should go. So here I have a lambda squared, which comes from this lambda squared. Then I have sai che scrivo il risultato direttamente, minus lambda e to beta epsilon, that comes from questo per questo, questo per questo, and I have 2 cos hyperbolic of beta h plus 2 hyperbolic of twice beta epsilon equal to 0. One should get this expression. Let me check some of the terms. 2 coseno iperbolico più 2 seno iperbolico più 2 beta epsilon. So from this, for instance, I get e to beta epsilon times e to beta epsilon, which is then I have minus e to 2 beta epsilon, and this provides us a hyperbolic sinus. Okay. And then I also use the rule of sum of angles in a hyperbolic cosine. Okay, you can use this guy. All right, so this is trivial. Okay, one can do it. So I can fix it. I need to do it. So now, okay, with the circular equation, I can get the 2 eigenvalues, and also this I'm going to run a little bit just to be sure that it's correct, this one. So if you try to do it, so check if it is correct. Okay, so now we can find the 2 eigenvalues, which are, so blah, 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 you solve these, and you get lambda plus minus, which is equal to t to beta epsilon. Here we have, of course, H beta H plus minus square root of H plus e to the minus 4 beta epsilon. Those are the two eigenvalues. Blah, 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 and blah, blah, blah. Okay, good. Now, among these two eigenvalues, one is with the plus and the other one is with the minus. And consider that z of c is lambda plus to the power of n to lambda minus to the power of n. Since n is a very large number, basically, I just need to take the eigenvalue with the plus, because this is larger. So lambda plus is larger than lambda minus, and if I do it to the power of n, it's much larger. Okay, so then I can neglect the lambda minus and just take lambda plus to the power of n if n is large. So I can neglect the negative, so the eigenvalue with the negative sign. It's smaller. Okay. Good. So once I've done this, I can write z of c, which is just now the positive, so the eigenvalue with the plus to the power of n, and therefore I have the final expression for the canonical partition function, which is beta epsilon n, and here we have cos h beta h plus square root of sine squared h beta h plus e to the minus 4 beta epsilon, and everything is to the power of n. So this is the canonical partition function, which contains all the thermodynamics, as we know, because now from this I can remember that the Helmholtz free energy, A, is Helmholtz free energy, is just minus kBt log of z. So the canonical partition function provides the Helmholtz free energy, which I'm going to write, and then we stop. So the Helmholtz free energy is the following. A is minus kBt. Then I have to do the log of this quantity. So I will have beta epsilon n. And then I have n, minus kBt beta epsilon, yes, plus n. And then I have the log of this quantity. So log of cosine of beta h plus the square root of sin squared h beta h plus e to the minus 4 beta epsilon. And that's it. This is the canonical, well, this is the Helmholtz free energy. And from this we can derive the thermodynamics. And can also divide by n here to take the Helmholtz free energy per particle. Okay. Now let's stop for a break and we will continue in 5 minutes. But it's remarkable the fact that we can get analytically the Helmholtz free energy, so the canonical partition function and the Helmholtz free energy without any assumption. Okay,
So let's stop for a break.
Okay. So let's continue with this expression for the so this is the Helmholtz free energy. We will use it later to compute, for instance, the internal energy and the heat capacity. But first of all, what I want to compute is the magnetization, which we call like M. So this is the magnetization. Which is equal by definition to the sum from K1 to N of Sk average, where the average is an ensemble average. Now, what we know from our experience is that once we have the canonical partition function, we can basically derive everything. And this is the case also for the magnetization, which is basically the sum over all the spins average in the ensemble. And indeed, if I take Z of C, the canonical partition function, let me just write it down, was S1 Sn of e to beta sum K1 to N of Sk plus 1 times e to beta H sum of Sk 1 to N is the original form for the Hamiltonian. And then you see here that if I take the derivative with respect to H of the logarithm of Z of C, well, since I have a log, I have 1 of Z of C, which provides the normalization. And if I derive with respect to H, I will just get a sum S1 Sn of e to beta, well, the same thing as before, Hamiltonian, and then since I'm deriving with respect to H, I will get here a beta and a sum from so K1 to N of Sk. Okay. So then if I put this beta here, 1 over beta, and remove it from here, you see that this is just the ensemble average of this quantity. This is basically the magnetization written here, okay? Because I have 1 over Z of C, and then here I have the structure e to beta H, okay? So this structure here corresponds to the trace, if you want, of e to minus beta H, where H is Hamiltonian, times the observable divided by the trace of e to minus beta H. In this case, the observable is the magnetization. Okay, so it has the structure of an average of an ensemble average. This one. Okay. So the magnetization is just this guy here. So M, the average magnetization. Sorry, here there is no this symbol. Just here. Sorry. So M is just 1 divided by beta derivative with respect to H of log of Z. So I can compute this magnetization by just taking the logarithm of the canonical partition function, then deriving with respect to H. Okay. Now this is also equal to 1 divided by beta derivative with respect to h of the log of C of T is just minus beta the Helmholtz free energy minus, and therefore this just will be minus the derivative of A with respect to H. Okay, and this is M. And if I want to compute, this is the important quantity. So the magnetization, the total magnetization divided by M, so per particle, if you want. So M divided by N is equal to minus the derivative with respect to H of A divided by N. So I just need to take the expression that I have above and then deriving with respect to H.
Prof,
Un attimo, non so che sta. Sì,
can you hear me?
sì, sì.
I have a question. Don't we have to consider in the definition of magnetization also the orbital part of the angular momentum of the particle?
Okay, yeah, in principle, yes, but here we are just considering a very simple system in which we have just the spin of those particles which are localized in a lattice. Okay, so there is no angular momentum, orbital angular momentum, because these are lattice. So we have some points in which I attach the spins, and that's it. Okay. So I need to do this calculation if I consider a gas of free particles, which or atoms, in which I need, of course, to consider the contribution of the spin and the angular momentum. But this is not the case because those particles are fixed. Okay, so the only quantity that couples with external field is just the spin of the particle.
Okay, thanks.
Ok. Voi avete capito che è successo che è venuta così come vabbè, che dire. Okay, so I have to do this derivative with respect to h of this quantity. So let's try to do it. Let's see, and I have a minus, so I have a kBt, which is this term here. And with a minus, I have a 1, and then I have, okay, to do this derivative, so but I have the cos h plus square root h plus e to the minus 4 beta epsilon. And I have to derive with respect to h this quantity. And so here I have beta sinus h of beta h. Okay. Then I have here 2 square root of beta h plus e to the minus 4 beta epsilon. Then I have a 2 beta h beta, and of course and I think that's it. So che cos'è? Il seno e la beta. Sto qua. Okay, so now, okay, it's a matter of calculation again. So this kBt, here I have this guy by this guy, which is, so the beta, yeah, I can simplify a beta, because this kBt beta can be removed. So So I will have the square root. I'm not going to write what is inside the square root. And I have a sinus h beta h plus twice beta h cos h beta h. And here we have cosine h beta h plus the square root and twice the square root. Okay. And that's it. Well, actually, yeah, the factor of 2 drops. Correct. Yes. Drops. I can collect a sem beta h here. And if I collect this, I get a cos plus the square root and a cos plus the square root, which simplifies. And then this term drops. Then finally, I have this expression for this magnetization per particle, which is the following. So m divided by n is equal to h beta h. Here I have the square root of what was here, which was the same, c h squared beta h plus e to the minus 4 beta epsilon. Di beta h diviso quello. Ok. Okay, so this is the magnetization per particle, which is found really analytically in this setup. Now let's make a plot of this quantity. So if we make a plot of m divided by n as a function of h, so as a function of the external field, so you see that from if h is equal to 0, I get 0. And if h goes to infinity, I have this diverges like this, and then I have 1. And if it goes to minus infinity, this minus 1, right? So the behavior will be something like this. So this is 1. This is minus 1. And I will have something like this. Suppose that this is for T1, for a certain value of the temperature. And if I do another temperature larger than this, I see from here that if at fixed h, if T is increased, the sinus h goes to 0. So then if T2 is larger than T1, I should get something like this. T2, if T2 larger than T1. Well, of course, at some point at infinity, we'll go to 1. Okay. So then what you notice is that basically there is no magnetization in the sense that there is no spontaneous magnetization. Let me write it down here. No spontaneous magnetization. because if H is equal to 0, then also the magnetization of my sample is equal to 0. Okay. What will be different in the Icing model in 2 dimension, for which instead we have magnetization below a certain value of the temperature, which is the critical temperature. So in 1 dimension, we do not have a magnetization, spontaneous magnetization, and so we do not have phase transition in this case. No phase transition. Okay. And there is an argument that I will present at the end for explaining why in 1 dimension, at least, there is no phase transition in this case. So basically, this material behaves in a paramagnetic way. Okay. If you want. In which if I increase the value of H, the external field, I get the final value of the magnetization in the same direction. And okay, if I decrease, or if I increase H to the negative direction, the magnetization will just follow the external field. Okay, and so this is a paramagnetic behavior, which is different from a ferromagnetic behavior and a diamagnetic behavior. The diamagnetism, as I said before, I will not do it this year because there is not enough time. Okay, so this is the first thing that one can notice. Then we can compute the thermodynamics. And in principle, we can compute anything. We will compute in the internal energy and the specific heat. Well, at least I will plan to do it. Maybe I will not compute it in detail, because it's just a matter of doing derivatives. So now, for you, internal energy, I have to do the minus the derivative of the log of 0 C with respect to beta, which is minus the derivative with respect to beta of minus beta A, which is equal to A plus beta derivative with respect to beta of A. Okay. Which is the standard formula in which U minus Ts is equal to A. So this factor here is just Ts. So it's temperature times the entropy. I consider the fact that beta derivative with respect to beta has to be translated into a derivative with respect to temperature. So let's compute this. At H equal to 0 in order to have a simple expression. So, and then for H equal to 0, what is A? Let me write it down. So A was minus, well, A divided by M was minus epsilon minus kBT. And the log of if H is equal to 1, you just have 1 here, and here I have a square root of 0 plus e to the minus 4 beta epsilon, which in this case is e to minus epsilon beta times 2. That's the expression for the Helmholtz free energy per particle in the case in which the external magnetic field is equal to 0. Okay. Okay, so now it's a matter of doing the calculation. Maybe it's not very interesting to do it. It's just making the derivative with respect to beta of this quantity. So u, well, u will be equal to minus n epsilon minus n kBT log 1 plus the minus epsilon beta. Then I have a plus beta. Then I have a factor of n which I can collect. And then I have to do the derivative of beta with respect to beta of this quantity. Vediamo se dt log beta n, we just catch the calculation. So here 1 divided by beta squared that comes from here because this is 1 minus beta. Log of 1 plus beta. Beta n quel termine lì, then I have the other 1 plus 1 divided by beta, need to do beta epsilon, 2 epsilon, and here I have 1 plus beta epsilon. That comes from the term, from the logarithm here. Okay, so this is just really computing. At the end, one finds this expression, which is very simple. U is equal to minus epsilon n, so this factor here, times tan h of beta epsilon. Okay, so this is the internal energy. Minus epsilon n times the hyperbolic tangent of beta epsilon. So now you notice that if t is large, at fixed epsilon, so if t is going to plus infinity, then u is equal to 0. Okay. Whereas if t is small, this tangent goes to 1, and therefore u is minus epsilon n. So if t is approaching 0, u becomes minus epsilon n. What does it mean? This is very intuitive, actually. It means that now we are considering the response of our sample with respect to exchange of heat, if you want, or by modifying the temperature. Before, instead, we were seeing what happens when I change the external magnetic field. Now, you see that if I increase the temperature, if the temperature is very large, U is equal to 0. What does it mean that U is equal to 0? So there's no external field, because this is the case that we are considering, and the energy was provided by the coupling among the pairs of spins. Now, this equal to 0 means basically that on average, of course, the spins are misaligned. So the spins are anti-parallel. Or if you want this offer. So there is no, it's like the case in which there is no magnetization. Okay? So we'll have some of them which are parallel, some of them which are anti-parallel. So in the average, basically, I do not have So remember that I have in the Hamiltonian a term which was like this. K sk plus 1. So some of them can be signed in such a way that sk times sk plus 1 is plus. So for others it can be minus, and therefore at the end the average is 0. Okay, so there is no order basically in this case. Whereas if you going to minus epsilon n correspond exactly to the opposite situation. So in which all of them are aligned, and you, in this case, go to minus epsilon n, which corresponds to the fact that here I have either plus plus or minus minus times epsilon. And I get minus epsilon n. Okay. So this corresponds to our intuition that when t is larger, I have disorder. There's no preferred direction for the spins. Whereas if t is going to 0, all the spins are aligned along a certain direction, which could be plus or minus. So in this respect, it's like having a critical temperature here or phase transition, but that occurs only when t is very small, so it is equal to 0. So only in that situation, all the spins are aligned. So if you want, the phase transition occurs, but at t equals 0, so it's not a real phase transition. So this is the only situation in which spins are aligned in one direction. Now one can compute, but I will not do it, the specific heat, just to make then a comparison with what happened in 2 dimensions, in the Icing model in 2 dimensions. But computing the specific heat is just a matter of calculation. Well, actually, it's not in this case, it's easy because U is minus epsilon n, the hyperbolic tangent of beta epsilon. Questo era U. And the specific heat, here just by tradition I write a fixed volume, although here the particles are fixed, so there's no volume as a variable. I cannot change the volume. So this is minus, sorry, is the derivative of U with respect to the temperature. And here just take these derivatives with respect to T, and you will get that CV divided by NKB in order to have high-dimensional quantity is equal to epsilon divided by kBT squared. Where does it come from? It comes from this 1 over beta, 1 over kBT, the argument. And then I have the hyperbolic squared of epsilon divided by kBT. So this is the specific heat as a function of temperature and coupling epsilon. If you make a plot, dV divided by NKB, we have a very smooth behavior of the heat capacity, which for T equal to 0 is going to 0 because I have this term that dominates, and also for T going to infinity is going to 0. Okay, so I have a smooth behavior of the heat capacity because there is no phase transition. And actually, we will see that in the Icing model in 2 dimensions, we will have actually some problems when computing the specific heat of the heat capacity. Now let's present an interesting argument for explaining why in 1 dimension we do not have phase transition. This comes directly from the analytical calculations that we have done, but there is a qualitative argument that is nice to present. So why no phase transition in 1D Icing model? Well, the thing is the following. Suppose that you start in a situation in which all the spins are aligned. Okay. You start with this configuration. And then decide to make the following. So to break this chain at a certain point and to invert all the spins in one direction from the right or from the left. So basically you take this, you break the spin at a certain point and you spin, and you flip all the spins, for instance, which are on the right of this line. And you ask yourself, which is the change of the Helmholtz free energy when doing this trick? So the Helmholtz free energy A is U minus TS. And so delta A will be a delta U minus T delta S. Now the thing is to compute the variation of internal energy and of entropy when doing the operation of flipping all the spins to the right of this separation. Okay. Now it's easy to convince himself that delta A, and we show why it's like that, is equal to delta U, which in this case is just 2 epsilon, minus T. And here I have AB log of n minus 1. Now let me explain why here we have the log of n minus 1. So these are variation of entropy. The variation of entropy must be Kb times the log, no? It's Kb times the log of how many ways I have here to separate the spins to have let's say some of them on the right and some of them on the left. I have n minus 1 way to separate the spins. So n minus 1 is the number of ways of separating the spins. Okay, so I can choose to flip all the spins that are on the right of the first spin, of the second, the third, etc. Okay, so I have n minus 1 ways to make this operation, and this n minus 1 ways contributes to the Boltzmann entropy in this way, no? So the log of the number of microstates corresponding to the same macro state. Okay, so since I have n minus 1 ways to do it, the variation of the entropy will be something like that. Okay, and so you see here that since n is large, this delta A will be dominated by this term here. Okay. So since n is large, delta A will be minimized by flipping the spins. In other terms, when I see which is the variation of the Helmholtz free energy, there is a positive contribution due to the fact that I'm not aligning the spins anymore. So this is a penalty, if you want, because the internal energy increases. But the Helmholtz free energy gets two contributions, one from the internal energy, one from the entropy. So the fact that we are increasing the internal energy is not important, because in any way you are compensating by a large increase of entropy. So you increase the internal, so by doing this flip, you increase the internal energy, but you increase a lot also the entropy. And so there is a minus here, and therefore if the increase of entropy is dominating, we actually minimize A, which is the Helmholtz free energy, by increasing the entropy in this case, therefore by flipping the spins, and so by not having any specific direction in which the spins are aligned. Okay. Now why? So this is the explanation for delta S. Why I have two epsilon here? Well, the fact that is that I'm losing pairs, no? So suppose that I have 4 spins, which are combined. Then the internal energy in this case will correspond to the fact that they have 1, 2, and 3 aligned pairs, so it will be -3 epsilon. Okay. Whereas if I have a situation like this, sorry, what your photo. So suppose that I have a situation like this in which I'm flipping all the spins in the right, then I will have that here internal energy will be, this is epsilon positive -2 epsilon, corresponding to the fact that I have 2 pairs now. So epsilon -2 epsilon, and which is minus epsilon. So now if I take the delta U, will be minus epsilon minus 3 epsilon. It will be this minus epsilon, which is equal to 2 epsilon. Okay. So when I do this flip, I get additional contribution to the internal energy, which is twice epsilon, which corresponds to the fact that we are losing pairs. No, here we have 2, 1, 2, 3 pairs, whereas here we have 1 and 2 pairs. But then we have this term which contributes with a positive epsilon, whereas those are contributing with a negative epsilon. Okay. So therefore, at the end, the balance, since I have to minimize the free energy for the second principle of thermodynamics, even if I'm increasing U, I'm increasing so much the entropy, because the entropy increases as the logarithm of n, whereas the energy increases by just this amount that does not depend on n. Therefore, at the end, it's better to have a system which is completely without magnetization. Okay, so that's the simple argument to explain why there is no phase transition in one dimension. Okay, so now next time, what we will do is to provide the version of the Icing model in 2 dimensions. Now the thing is the story is much more complicated. Actually, one can look, but we are not going to do it, at the analytical solution for the 2 dimensions, which is the Onsager solution. If you are interested, you can have a look to the book of Carson Wang, in which there is the derivation of the solution for the 2T Icing model. Solution of Onsager. But we are going instead to compute it by using the so-called Midfield Approximation. For us, okay? And we will see that even at Midfield Approximation, we can capture the main qualitative features of a phase transition, and so of the fact that at a certain value of the temperature, finite value of the temperature, we have a spontaneous magnetization that we do not have in one dimension. Okay. Now the situation is more complicated because we are in two dimensions. So I imagine my lattice of being something like this. And therefore, here the situation is much more complicated because, for instance, for each particle, I have the closest that are 1, 2, 3, and 4. Then there are the little bit less closest that are this one, and so on and so forth. So I have a hierarchy of interactions between one spin and all the other particles. That is much more complicated with respect to the previous case. Okay. And in particular, the results will depend also on how many particles the spin are interacting with. Così Luciano è contento e finisco in tempo. See you. Bye bye.
Arrivederci.
Ciao. Interrompi la registrazione. Così.